Okay. So before I finish off the example that I was involving my complex multiplication, if you remember that one, I was going to clarify a couple of things just because when I had the office hours last week, it made me realize, okay, like maybe like this stuff about bilinearity and things like that, maybe it's still a bit confusing. So like just to kind of like make it more clear, like what I mean by that, with things that you already know. So like and then I can kind of like continue talking about the complex multiplication stuff. Okay, so here's like an example that you know pretty well, like say the dot product, because you have like saw that in Calc 3. So I'll even write them in terms of like I, J, and K. So if you have like a vector which is U1 I plus U2 J plus U3 K, right? And V is V1 I plus V2 J plus V3 K. Well, if you wanted to do the dot product, U dot V, okay? Well, hopefully you remember this, but one of the properties of the dot product is that, the distributive property holds. Okay, so you could, the distributive property holds. So if you wanted to find the dot product between two arbitrary vectors, if you use the distributive property, what does that give you? That gives you um, U1 V1 I dot I plus U1 V2 I dot J plus U1 V3 I dot K, and then you do the same for the others. U2 V1 I dot, sorry, J dot I, right, plus U2 V2 J dot J, um, plus U2 V3 J dot K, plus U3 K, so sorry, U3 V1 K dot I, I'm almost done. U3 V2 K dot J plus U3 V3 K dot K. Right, like if that's like the most general way you like, if you use the fact that the dot product is distributed, then you can find like the dot product between two vectors, right? So if you notice carefully what this is saying is that to know the dot product between arbitrary vectors, really it all boils down to knowing the dot product between I, J, and K, right? If you know like the values for the dot products between I, J, and K, then you're done. Uh, so here, like, if you know all of these possibilities, then you would have your answer. In the case of the dot product, right, what happens is that the way it's defined, if the vectors happen to be orthogonal, you get zero, right? So that's why you don't see this term nor this, like all the ones except I dot I, J dot J, and K dot K go away, right? And then like the overwhelming majority of them are zero, right? So this one is zero, 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 this one is zero. But and then the others are one, right? Like this one is one, this one is one, and this one is one. And so this is ends up being U1 V1 plus U2 V2 plus U3 V3, right? But all that I'm saying is that in principle, that formula is kind of like a consequence of you requiring the dot product to be distributive, right? And just specifying how the dot product is supposed to behave on the basis, like the usual basis I, J, and K. Does that make sense? Now, how do you interpret this like in the terminology that I'm using with the tensors and all this stuff? So from the tensor perspective, right? From like the tensor perspective, so here's like the tensor interpretation of this. You have an operation, let's call it capital D for dot. Okay, so you have an operation called D that it's two vectors with three entries, right? It spits out a number, right? Because the dot product is a scalar. And basically what it does, yeah, sorry, U1, U2, U3. U1, U2, U3, and then V1, V2, V3. And gives you V1, V1 plus U2, V2 plus U3, V3. Right? So, but from this perspective, like there's a map, right? Which is a dot product that the input is two vectors and it spit out a number. But each of them, but the idea is that this map is bilinear, So it is a bilinear, this is a bilinear map. So this is bilinear. And again, what does being bilinear means? It means that if you had d of u plus u prime, comma v, that's the same as d of u, comma v plus d of u prime, comma v, which in this case, if you write it down in the of what it means in case of the dot product, it just means that you're doing u plus u prime dot v, right? This is just what bilinear means. So it's just like the distributive property, right? And same goes with the other entry, right? So like if you had like d of u v plus v prime, this is d of u comma v plus d of u comma v prime, which again is just like the fact that u dot v plus v prime is u dot v plus u dot v prime. So, kind of saying that the dot product was a distributive operation is in like a less fancy way of saying that the dot product is a bilinear operation. Now that's how we're thinking about it, kind of like in a more like abstract version level of what the dot product is. And being bilinear, because it's bilinear, it means that it is completely determined by what happens on the basis. So being bilinear, because of bilinearity, that means that because it's bilinear, since D is bilinear, it is determined by D of E1, E1, D of E1, E2. Now I'm switching back to the usual notation, or like, I mean, I guess I could still, let's just use like, instead of IJK, I'm just putting it like, like E1 is I, E2 is J, and E3 is K. Uh, okay. So, and of course, like if this is super annoying to write down, like, so that's where the indices come in, because then basically another way of saying is that another way of saying this is that to know what the dot product does, what you need to know, so you need to know D of EI, EJ, where I and J go from 1 to 3, right? Each I and J could be 1. So you need to know like all the possible dot products between the bases. This is what this is there. Is that okay? Is that making sense? Everyone with me up to this point? And so if you want, so what I'm saying is that from this perspective, the dot product itself is a tensor. The map itself is a tensor. So D, the dot product D, as a multilinear map, as a bilinear map, is a tensor. Okay, but if you go back to like the more you know, old-fashioned way of thinking of what a tensor is, like as a collection of numbers. In this case, the collection of numbers are all these possibilities that you have, because and so the tensor has two entries, which you could call di sub j. So in this case, actually, it will be because it has two indices, it would be represented by a matrix. So you can represent the dot product itself as a matrix. That's kind of like the point. So it would be, in this case, it's like a 3 by 3 matrix. And well, I had that's why I think I may have mentioned that I have updated the problems on the PDF, but I didn't ask you to finish any of them new ones because I was waiting until we had this discussion, because one of the problems is for you to find the entries of this matrix, which should be relatively straightforward, but it's kind of like just to make sure like we're kind of like understanding what like it's saying. But this is kind of like the matrix representation of the dot product. That's one way to think about it. Yeah.
So the operation that you do with quantum matrix, so the two vectors you have one matrix
Oh, well, right. Like, so the idea is that if you kind of, just to go back to the tensor notation, if you, okay, so if I'm saying this is a tensor, right? If the way we were drawing it, like at the very beginning of the class, at the start of the course, right? It has two legs, or like two, two edges, right? So that means that you can feed two vectors to it, right? And if you feed one of the vectors, call it u, that has entries, indexed by I, and the other vector that, um, call it v, that has entries indexed by j. If you remember, like the way this is done is kind of like a big sum. You do like the multiplications of I and j. So this will give you, this corresponds to kind of like a sum of I and j to 3 of, like, dij, vi, well, I guess ui, bj. And the idea is that basically the way you choose the entries of this matrix will be that this actually matches u dot v. Like this will be the same as doing like u dot v. So the tensor contraction would give you the same as result of the applying the dot product to the two vectors. That's how it's defined. Is that making sense? Okay, so here's where it gets more interesting, because then you can, and before I return to the matrix, to the complex multiplication, uh, you can, if you think about another operation that you know from Calc 3, like for example, the cross product, right? You can do exactly the same story for the cross product. So I'll kind of like do like a summarized version, right? Like you can take, I'll call it C for cross product, So the cross product, one way to think about it is that you eat two vectors in R3, but now you produce a vector in R3, right? Because a cross product is, a new vector, not a number. But the idea is that, if you give me a vector u and you give me a vector v, I can send it to u cross v, right? But the cross product is still distributive if you remember like the properties of the cross product. You can still distribute with the cross product, which translates into saying that you only need to know what the cross product does between I, j, and k. You know, I cross I cross j, I cross k, blah 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 blah, j cross j, all these like possibilities is so because the cross product is bilinear, so this one is bilinear as well. So it is fully specified by what it does on the basis, by C of it's basically the same, right? By C of EI EJ. Okay, where I equals well, actually I'll call them J and K, you'll see, just to kind of be consistent with how I wrote them on the notes. Okay. And J and K are just like, could be 1 to 3, right? Like, so this is just saying that you need to know all the possible cross products between the basis vectors, right? Now, my point is that because this is bilinear, this is a tensor, right? So there's kind of like a tensor, like you can find the tensor entries of the cross product. But here you have to be a bit more careful because the difference now is that this represents the cross product between EJ and EK. So this is actually a vector, not a number, right? This has entries because this is just like the name, this lands somewhere in R3, like, just to be a bit more precise, like this is EJ cross EK, right? Like this is what I mean by, sorry, like let me write it like this so that it's a little bit less confusing. So I'm just saying EJ cross EK is what I'm calling C of EJ cross EK. So the thing is that this itself has 3 entries, right? Each of these things has 3 entries. So each of them has 3 entries. Each has 3 entries because it's a vector in R3. Being a vector in R3. So if you wanted to define the entries of the tensor, right, you need 3 indices. You need 2 indices to specify the vectors themselves that you're talking about, and you need an extra index to refer to the entry of this thing. So that's why there's a third index that pops out in this case. So this one way to think about it is like entry I of the vector C of EJ, EK. Okay, so the difference is like in the cross product case, because the cross product already produces a number, there's no further specification needed. But in the case of the cross product produces a vector. So you need to also be able to refer to, which value of the entries of the cross product you're talking about. Okay. And this actually is a famous tensor in physics. It's called the Levi-Civita tensor E epsilon IJK. So I mean, I'm just using like a weird notation so that it doesn't seem like a spoil. This is what the physicists called. This is called the Levi-Civita. It's called epsilon IJK by the physicists. But all that I wanted you to notice is that it kind of like it gets an extra index because now you need an extra index to locate the entry of the vector, right? Because the entries of a tensor should always be real numbers. We're not considering vectors as possible entries. So that's why the extra index comes from. So in this case, it's like a box. It's like a 3 by 3 by 3 box. So it's literally like a cube, like this tensor. Like, so it's like a 3 by 3 by 3 box or cube. Is that making sense? Kind of like more so far so good. By the way, because like come up during the office hours, you would if depending on where you read this stuff, um, they use the word rank differently from how I'm using it. So the way I would refer to this is that because this has 3 indices, I would call this an order 3 tensor. Some references say that this has a rank 3 tensor, which is not completely different from how I'm using the word rank. So I would call this like an order 3 tensor, but I'll just make a remark that what I'm calling order, some people call rank. So you just have to be careful with that because rank has like a very precise meaning in our context. So this is called like an order 3 tensor. But some references call this rank. So just be careful with that. Okay. So for me, like the order doesn't from anything that you need to specify the point that. Okay, and then now back to the case of complex multiplication. Unless there are any questions about this. I just wanted to clarify this bilinearity property. So that's kind of how bilinearity plays a role in these things. Like, the point of being bilinear, that one of the advantages of being bilinear is that then to know what it does, you only need to know what it does on like, combinations of the basis vectors, basically. And so back to the complex multiplication case. So the idea, let me see like how I'm not sure if I call this M. Also, let me just stop and check. Yeah, I think I call it M for multiplication. So, okay. So the idea is that you had M, which goes from R, like again, it eats two things in R2 and it produces two things in R2. The way that you wanted to think about it in this case, or maybe it was T last time, but it doesn't matter, is that you have a complex number, but you can think of a complex number, as a pair, A comma B, on the plane, and you have another complex number, which is another pair, A comma B on the plane, and you send this to the multiplication or like the product of these two complex numbers, which is just C times W. If you work out what it is in terms of the entries on the plane, that gives you that weird formula that I had written before, gives you AC minus BD, BC plus AD. Okay. Which is kind of weird to figure out, but if you kind of like rewrite this as, A plus BI, if you write the complex number as A plus BI, and you write this complex number as C plus ID, then you multiply them and you just play with it and you find that formula that I had written last time. Okay, and so again, the point is that this is fully specified, the multiplication, because this is bilinear. This is fully specified on what it does on the basis of R2. So M is specified. Once you know M of EJ, EK, where K and J go from 1 to 2. But again, there's a multiplication of the two vectors as complex numbers. And so these lands in R2. So you need an extra index to just refer to the entry that you obtained. So that's why that tensor had three entries last time. So that's why I had defined Mij(k) to be the entry I of the product Mij(ek). So again, this is 2 by 2 by 2, right? Because it's all like on R2. So it's kind of like a cube with 8 entries. This is a 2 by 2 by 2 tensor, or like kind of like a cube. And it's order 3 because it has 3 indices.
What portion is problem, you recommend a lot of it to die and figure out what happened.
Well, I mean, in these problems, like the thing is like with the tensor diagram is, like usually like it's, unless you have the tensor as a collection of numbers, right? If you have like the formula first, if you have the formula first, then you would define the entries of the tensor, right? But yeah, I guess it's possible that you would have the entries first, in which case, you can just maybe work directly with the tensor diagram, but like in general, you probably start, at least for this example that I'm constructing right now, you can like start with the formula, like kind of like the formula, and then you find kind of like the entries of it. But I mean, like in a we will return back more to the tensor diagram stuff after this one or two class, because I'm just like, I just wanted the grants on all this stuff to kind of be made more clear before we kind of like dig deeper into the, the tensor network stuff and like, but yeah, so that's why I'm doing this. Now, what I was going to say, like, and I think I had found this like before, like, or at least I wrote like what the answers were. So, you can kind of like check that like the entries are M11, which is 1, M211, which is 0, M112, which is 0, M212, which is 1, then M121, which is 0, M221, which is 1, and then M122, which is -1, and M222, which is 0. And just to kind of like clarify how you would figure out these entries, let's do the one that gives you -1, because that's kind of like maybe the more interesting one. So for example, what was the meaning of this? Like, what was the meaning of this entry? So M122 is the first entry, right? Like this first index refers to the entry you're referring to. So this was like the first entry of M of E2, E2. So like the last two indices refer to what you're multiplying here. Okay. So again, this is kind of like complex multiplication. So the idea is like E2, right? E2 is like 0, 1, and 0, 1. But if you want to multiply them as complex numbers, 0, 1 corresponds to I. So you're doing I times I. And I squared, if you remember, is -1. But again, if you want to rewrite this as a complex, as a point on R2, it's -1, 0. And that's where you see, because I wanted the first entry, that's why I'm putting up the -1 here. So that's where like the -1 comes from. And the second entry gives you 0, which is what you see there. And so you can like figure them all out that way. Yeah.
So, yes, for like the tensor product, we also multiply it here, tensor, so like assuming we use matrices as tensor for that.
Oh yeah, you
free.
you can yeah, you can I mean this operation of multiplication is like, the tensor product is like a different type of multiplication, right? But yeah, you can still like the tensor product is multilinear in this way, right? Yeah.
You have to define though every single version.
I mean, there is not like there is like a more like abstract definition of the tensor product. Yeah, but then like a specific examples, we have to show that it's like the abstract definition. Actually, I was going to give an example for functions. So you can define the tensor product of functions of one of the things I was going to mention in a moment, and maybe relate that to Boolean functions, we can make a fun topic. But yeah, once I get to the example of function, I'll say more about that.
So we can find the order just by looking at the back.
Right. Yes,
If we have like two vectors that are joining in with the tensor knowing. And it has to be the vector, and it has to have the tensor node has 3 edges between the order and the.
Yeah, like I mean, if you have a tensor diagram, you can always read off the order very easily because it's a number of three legs or like non-contracted legs. So for example, I think we had like done some of these. If I have like a tensor like this, because it has 4 legs, right? It would be order 4, right? But imagine then you want to kind of like take the same one, right? Take this tensor, and you want to remove 2 of the legs. So you could remove 2 of the legs by feeding a vector to each leg, or even you can feed a matrix to it because the matrix has 2 indices, right? So for example, one way you could kind of like take a matrix like a matrix which has order 2 from this definition, and then you're left with something of order 2, and then this would become a two matrix, not a two tensor, which is a matrix, right? So, but yeah, from like that's kind of one of the advantages of the tensor diagram notation, that it is very easy to kind of like keep track of how many, like what the order of the resulting thing ends up being. Yeah.
M of J, M of EJ failed. Sorry, M of EJ, comma, E failed. That is just, that just depends on our definition of what M does. Like, we can just
Correct.
map that to whatever we want. In this case, we just wanted it to be the pocket.
Exactly. Yeah. Right. So in the first example, it was the dot product of EJ with EK. In the second example, it was the cross product of EJ with EK. In this example, it's kind of like the complex multiplication, but that one only works in R2, right? Because only in R2 you can kind of like identify the vectors with complex numbers. But yeah, so the important thing is that that's the point, like in this case of being bilinear, that once you know what it does on the basis, on the pairs of the basis, then you know everything about the map. But it does depend on the specifics of the map, what the entries end up looking like. Okay.
What it does on the basis is like, it's up to us, whatever.
Correct. Basically, it is arbitrary. Yeah. As long as you, you can let it be whatever it wants to be. Like it's fully specific. It's completely arbitrary, and that would define like as yes, because as long as you impose the condition of it being bilinear, then it's up to you. How it's defined. Yeah. And then, what I was going to say is that there is a convenient way to, so these are 8 numbers, like you could draw them as a box. That's kind of like annoying. So one way to kind of like draw them in a different way is kind of like 4 and 4, so you can call them like pages of the tensor. If you thought of like the tensor being like a cube, like kind of like the front page and the back page. So you can arrange, just to make the numbers more nicely, you can like page, like I'll call them pages, like I equals 1. So this would be like, these 4 numbers. So I'm setting I equal to 1, and then I just use, for the last 2 indices, I just use like the usual matrix convention, first entry, first row, first column, first row, second column, second row, first column, and second, right? And so, it just looks a little bit easier to understand what you're talking about, because otherwise it just looks like, and somewhat, like amorphous array, and then the page I equals 2. Oh, sorry, let me use a different color just to kind of like confuse them. Page I equals 2 would be like this one, and that one, right? And that gives you some better understanding, of what the tensor looks like, somehow it feels more organized this way, And then the idea is like if you were to draw it as a cube, this is kind of like the one first page facing you, and then this kind of like is literally on the back, and depending on how you're arranged it. So that looks cool, right? Okay. And then we can ask, for example, what would be the rank, what is the rank of this tensor, right? So then the question could become, what is the rank of the tensor? Okay, so next question is, what is the rank of the tensor M? Okay. So for example, I don't know if I already gave this a problem, but I did write it on the PDF, but I do want you to try it out. For example, if you thought that the rank is 1, right? If the rank were 1, if the rank of M is 1, What does that mean? That means that you can find vectors in R2. You can find 3 vectors in R2. Then you can find vectors U, V, W in R2 for which uh for which M is U tensor V tensor W. Okay? And again, if you can be a bit more precise on what that means. What that means, what does that mean? It means that the entry ijk of this tensor, right? This means that if you remember how the tensor product works, it's basically all the possible multiplications between all the possible entries, like So it would be that ui with times vj times wk. So like that's how that means like the entry, ijk of this tensor is just like the product of like the possible products of the entries of the vectors. Okay. And in this case, I mean, so the problem that I asked you to she's like to show explicitly that cannot be done in this case, that should be easy to do because most of the entries are zero. And you can like do it by contradiction. We should get like something impossible very quickly because many of the entries of this are zero and one and negative one. So it shouldn't be too hard to work it out to see that that cannot happen. Uh, this way. Um, so. But okay, but then yeah, like I left it as an assignment, so like you can try it out. I'll probably make them do next week, but just try it, check like that it's impossible to satisfy these equations. Uh, check this doesn't happen in this case. Right, because you do know this particular entry, so that gives you a system of equations that you will need to satisfy, and you just show that that's impossible.
This one.
Well, for this particular tensor, for the tensor that I'm calling n, which aims from multiplying the complex number, I'm saying for that particular one, it's not rank one. Yeah, this particular, like, I'm now still talking about just like this particular tensor. Uh, but when you can show explicitly that it is rank 3, for example, this one is rank 3, uh, so but m is rank 3. And so what does it, again, I'm just going through this so that you see like, what it means in practice. So what does it mean to be rank 3? It actually means that you can find 9 vectors, okay? So this means a, I won't be too clever with the notation for the vectors because I'm going to write it explicitly in a moment. So, you have 9 vectors for which M is, A tensor B, tensor C, plus D tensor E, tensor F, plus G tensor H, tensor I. So what I mean, being ranked 3 means that it is a sum of 3 of these type of products, and that would be like kind of like the smallest number that we can find. Uh,
Could it also be like, three vectors but just different orientations, like?
Well, it depends here what you mean by, I mean, there can definitely be repetitions, but I'm not trying to suggest.
Yeah.
That, oh, yeah, no, I'm actually about to write. Exactly, I just mean like, you know, yes, like maybe it's good to, coincidences are allowed, right? So there could be repetition. So yeah, I don't meant these things, sorry about that. None. I just meant like, it is three triples, you know what I mean? So like that was like a way to say that issue, but it is allowed for all of them to be different, right? So I do want, that's why I wrote them with different letters. But yes, it's a good point. Repetitions allowed. In fact, in this case, like, it so happens that this is 0, 1 tensor with 1, 1 tensor with 1, 1 plus 1, -1 tensor with 1, 0 tensor with 1, 0 plus -1, -1 tensor with 0, 1 tensor with 0, 1. So you see, like, some of the factors do get like like some of the vectors are being repeated, yeah, sure. I mean, there's like, how do you find these vectors? It's obviously like an interesting question. It kind of like comes out, if you kind of like, I don't know if you remember from last time when we talked about the multiplication of complex numbers, and there's a way to rewrite it so that it only involves 3 multiplications instead of 4. So if you kind of like work out with that formula, you can kind of like extract out the terms, but it's a bit of a detour to what I'm interested in right now. I just wanted to give like an actual example of some tensor that was more than rank 1. I just wanted you to see that they are very natural, there's nothing like weird about them. They kind of like come out very naturally. And but it is true that the rank being 3 is related to the fact that you can multiply two complex numbers using 3 instead of 4 multiplications. Which is like 4 is like kind of like the natural assumption, but 3 you can do it like with 3. So rank being 3, is related to the fact. I think I had actually written, let me see if I can rewrite it again, so that you can see it. Where do I? Oh, yeah. The product of two complex numbers, you can write it as what? As AC minus BD plus I, A plus B times C plus D minus AC minus BD. So this only requires 3 multiplications. 3 distinct multiplications. Right? What are the products that you need to compute here? The products that you need to compute here are AC. You definitely need AC. That's 1 multiplication. Then you need BC. That's a second multiplication. And then you need to do AB times CD. So that's the third multiplication. So, the reason why I'm doing the example is because the bracket, in this case, is related to kind of like how many operations, at least in multiplications, it was required to complete the math. So it's kind of like a measure of complexity of some sort, like, how much time it would take you to find that. Multiplication.
So can you have an answer written as like several different like maybe this is one of the way to get this answer, but there can be like other sums of other vectors.
Yeah. So there are some conditions where like the composition is unique, but that's not too common. So yeah, like it is possible that it can be re-expressed as sum of 3 different triples, like if that's what you're asking. But the rank would be really the same, because just by definition, the rank is the minimum number of summands that you need. But yeah, the tensor composition is not always unique. You do need extra assumptions of for the uniqueness of the factors. Like
Is there like some like how many you need?
I mean, definitely like it sometimes like actually when we talk about the singular value decomposition for matrices and all that stuff, we can discuss that more, because in that one is more unique in a sense. But Yeah, like it depending on the problem, like there's some nice examples in statistics, where like they do have like the if the factors are kind of like unique decompositions, roughly it quotes, like then it does have like a useful interpretation about, the tensor. So it's definitely nice to have it whenever it's possible, but I'm just saying like you should think that it would always like, occur. Like most likely it won't be unique and new.
Also, are we gonna get into like, are there any algorithms to find that
Well,
agent?
like I'm not sure if I would. It may be more into the weeks. I do want to get eventually. Okay, so maybe I should kind of like say what my plan is. Like, I suppose at some point I should kind of like discuss. I do want to do an example of like that because it's supposed to be really relate to machine learning. So I do want to have an example where we kind of like use tensor networks to kind of like train like you have this problem like a binary sequence and you want to kind of like learn like you want kind of like the machine to kind of like predict what the frequency of the strings are, like based on some like samples that you feed to it. And there's like a nice way to do it with tensor, which is very elegant. So I would like to get to that, because it's not super complicated, and so it's kind of like more down to earth, which is what I like. So basically, like kind of like my goal for the next few weeks is that after I do the singular value decomposition, I'll tell you a little bit of probability just because we do need a little bit of probability to understand this stuff. And then we could move into this example of like the strings and the binary sequences. And then based on how much time we have left, then we kind of reassess but definitely like there are some algorithms like for like how to do these things like or how to try to find these factors to some extent, but yeah, I wouldn't prioritize that just because I do want to have kind of like a more machine learning type example. What I like about this one with the strings is that it does also have some connections with quantum mechanics just because some of the like some of the ideas do come from there. So it's kind of like you two birds with one stone kind of thing where it also allow me to introduce some stuff about some quantum mechanics. But yeah, like after I'm done with some of like the singular value decomposition and the others, three tensors, which is something that we need to know. I'll say a little bit about probability, and then I think we should have enough to understand that example. And then, I don't know where that would leave us by the end of, how much many classes will be left, and then to get over to assess, what topics you're more interested in. But I think that's a good one to, the other reason why this a good one is because one of the authors works at the Simons Institute, which is like Flatiron, like in Manhattan. So I can have like a worker here in the physics department. I'm trying to see if we can get one of them here to give I mean, maybe not a different paper, but it would be like a fun opportunity, for everyone to interact with someone who kind of doing research on that area. So I'll try to kind of like, I'm working on that, see if I can get in touch with me. So that way you can ask questions about like, research works, and all this stuff. And so I like the fact that I don't like in that job in our vicinity, but yeah, and then after that we'll see, how much time is left. But definitely on the Canvas side, they are. If you go down the dark web of the Canvas side, like you see like some of those papers they'll do refer about how to contract, optimize, or how to find like the rank, like approximate the ranks and all this stuff. At least I'll say something about efficiency with tensor contractions for sure, but I don't know how much I'll get into those specifics. That's kind of my plan for the next conference. Maybe to kind of like finish today with the last thing I wanted to say. Here's another cool example with matrix multiplication, which I had promised a lot to talk about this one, which is also very like surprising, Okay. So again, and this one will be the last thing that I write. So matrix multiplication. And I'll do it just with the 2x2 case. So if you have two matrices, A, which is A1, A12, A21, A22, and B, which is B11, B12, B21, B22. And then what is A times B? A times B, well, if you just work it out, you'll do A11, B11 plus A12, B21, and then A11, B12 plus A12, B22. Okay, and then A21, B11 plus A22, B21, and then A21 I mean, hopefully I didn't make a mistake, but just if I did, well, you know kind of what I'm trying to write of plus A22, B22. Okay. The only reason why I'm writing this explicitly is that, you could call this like the naive matrix multiplication, but that's definitely the one that we learned in like in linear algebra. And if you just count, you literally can see it's 1, 2, 3, 4, 5, 6, 7, 8 distinct multiplication principle. Right? So the way you do like the regular matrix multiplication involves like 8 multiplications. So this involves 8 multiplications. But there's like this other way of multiplying matrices that Strassen found that only requires 7 distinct multiplications. So I could write, I mean, it takes some time to write them down, but if you go to Wikipedia and just write Strassen's matrix multiplication, there is a way to multiply the matrices that only involve 7 distinct multiplications. So in Strassen, and funny enough, he was trying to show that it was impossible. So it's kind of like he actually wanted to prove that you could not do it with 7, and he realized, oh, actually you can do it with 7. So this shows that these things are hard, right? Because wasn't obvious that you would get it to work. So it's kind of like an interesting story. So you can do it only with 7, and it does have like some very useful implications for speeding up matrix multiplication, because if you have like 8 by 8 matrices, then 8 is 2 to the 3, so you can write it as matrix block form, and then you do some tricks, and then you can kind of like take advantage of the method to improve like how much time it takes to do matrix multiplications. The only reason why I'm bringing this up is that you then, from our perspective of like the tensor stuff, there is a map. I'll call it S for Strassen, which can basically it's 2 matrices of size 2 by 2, right? Let's just say mat 2. Right. So it is a 2 by 2 matrix. It is a 2 by 2 matrix. It produces a 2 by 2 matrix, right? What's the map? You feed a matrix A and B, and it spits out the matrix A times B, right? So this is bilinear, as you might imagine, right? Like this would be bilinear. Okay. And because it's bilinear, it can be represented by a tensor. This one does require way more indices. So it can be represented by a tensor. But the idea is that the only thing I want to say about this one is that it has rank 7. So the important thing is that it has rank 7, and that's related to the fact that the number of multiplications actually needed to do the matrix product is 7. So and it has rank 7. So the idea, like the reason why I'm mentioning this is that what hopefully this shows is that kind of like the tensor rank is some sort of like good proxy for the complexity of the map in some way. If you think kind of like that multiplication is kind of like the more expensive operation that, in terms of arithmetic operations, if you think of multiplication as being harder than sum, like, you want to see how many multiplications are involved. So the tensor rank is kind of like a good formalization of like, number of multiplications needed to do for a map. Rank is a good proxy. So hopefully this gives you kind of like a sense that it is actually like a useful thing to have around. Uh,
In order to be six.
well, okay, it depends on, the thing is that you have to be careful because the matrix is 2 by 2, right? Let's think about it. What is the basis for the 2 by 2 matrices? Like, you need, it has four, like what is the basis? Yeah, I guess you could do it with 6 indices, right? That's what you're thinking of.
E2.
Exactly, like kind of row, exactly, row and column. Yeah. So yeah, like because you have like this canonical basis, like which were like called EIJ, right? Like, so for example, E11 is 1 0 0 0, right? E12 is 0 1 0 0. E21 is 0 0 1 0, and E22 is 0 0 0 1, right? And every 2 by 2 matrix it can be described in terms of these four bases. Sorry, four matrices. So right, if you want to understand the multiplication map, you need to know what happens when you multiply two of these. So this would be kind of like JK, for example. JK, that's one of the bases, and the other basis is kind of like LM. And then, yeah, right, but this is a 2 by 2 matrix, so it has two more indices required to specify it. Yeah, like my indices are terrible in this case, right? So like the tensor has like A, B, G, K, L, M. So this would be entry A comma B of, like it's a bit of a mess. Or something like that. Because like again, like because now right, like the matrix, like, because you land in the world of matrices, so you need to specify the row and the column of that matrix. And then, yes, so I think, yeah, you can pull it off, I guess with 6 indices, yes, that's. And the idea is that, and then, each of these has two values, right? Because two rows, I mean, each row can be 1, 2, or each column can be 1, 2. So this was, we have 2 times 2 times 2 times 2 times 2 times 2, like, 2 to the 6 and 2 to the 6, oh, that's 64, if I'm not mistaken. Yeah, so it would have like, 64 entries, so. Counting the number of entries is like the most important thing because like, in a sense, like you can always we will talk about that later, but if you have a tensor, you can kind of like matricize it, which is kind of like a way of saying like let's just rearrange the entries as a matrix or like vectorize it. So they're like, like the presentation can look different. But yeah, like in terms of number of entries, um uh that seems okay. So yeah, because that's the same as 4 times 4 times 4, right? So yeah. That's another way to think about this. This is 4 times 4 times 4. Why is it a more useful way to think about this? Because each factor has a dimension as a vector space that it has. So kind of like the number of entries of the tensor is a product of the dimensions of all the vector spaces that you see here. So the number of entries of the tensor is the product of the dimensions of the vector spaces. So the space of 2 by 2 matrices has a dimension 4. So 4 times 4 times 4 is 64, and that's for like the 2 to the 6 of the time. But it's kind of like, you see, you kind of get used to kind of like thinking, oh, how many indices would I require? And it's kind of like fun thing to consider. But this is like a big complicated thing, very high dimension.
Hopefully, actually,
No, the matrix is not dimension 4, right? Because the 4 basis bit.
oh,
Right, 2 by 2.
oh,
2 by 2 is 4 entries, right? 4 independent entries, so it's dimension 4. Yeah. So it's 4 times 4 times 4. Okay, let's finish here. And again, if someone wants to ask me anything else specifically, I can answer your questions. I also have office hours starting soon. But now that I kind of went a little bit better on like the terminology and all this stuff, yeah, I'll kind of like tell you which problems you can work on. But I'll let you submit them like next week so that you have enough time to think about them. But I think hopefully this class clarifies some stuff about like terminology and how this is supposed to look like. But yeah, let's end here. Let me stop the recording.